Hello, and welcome to my recording of the Measure Your Height Lab. My name is Ellie Andrew-Vaughan, and I'm a student at the University of Massachusetts Amherst during summer of 2022. Right. The goal of this experiment is to accurately measure my own height using three different methods, all of which are based in physics. The first method is going to find the area under the curve of a velocity graph using the iOLAB software. The second method is going to use constant acceleration with the iOLAB device using an accelerometer. And the third method is using constant acceleration, just using a penny and a stopwatch. I'm going to take you through each of these methods, and then at the end, I'm going to talk about how they each compare to one another and whether or not they were accurate. So, the first method is to find the area under a velocity graph. So the first thing that I did was I found a board that was taller than myself, and I drew a line on it with my height. I had to actually change the board that I was using because originally the board was only about an inch taller than myself, and I needed to have it be much taller than that so that I could fit the entire iOLAB device before the start line, which was the line that my actual height was drawn at. Then I took the iOLAB device, I turned on a recording using the wheel feature of the iOLAB software, and I placed it so that the very front of the iOLAB device was exactly aligned to that line that I drew representing my height. After that, I pushed the iOLAB device in a straight line while recording, and then I stopped pushing when the very front of the device reached the end of the board. This means that the little wheel that was actually recording was pushed the exact distance that was my height. Finally, I went into the iOLAB device software and I found the area under the curve, which I will show you in a moment. The data that I collected was the area under the curve, which was in meters, and I'm assuming that my start and stop positions were perfectly lined up. I might have had a little bit of human error in there, and I'm also assuming that there's minimal friction acting on the wheel from inside the iOLAB device itself. All right. So this is the sample data from the iOLAB software for this first method. This is what you can see. This is the velocity versus time graph. And the area under this curve is the distance in meters that the device traveled. So that means that the area under this curve is my height. You'll notice this is the place where I started pushing, this is the place where I stopped pushing, and I didn't use a constant velocity because it's not necessary. The software was able to actually calculate the area under this curve for me without me requiring that I use any sort of constant velocity. The area under the curve, as you can see, is right here in this box. So I am 1.603 meters tall, according to this trial of this method. I did a total of 5 trials for each of the methods. This is the first method. On average, I found that I'm 1.6008 meters tall, or 160.08 centimeters. That is fairly accurate because my actual height measured using a tape measure is 160 centimeters. So I'm impressed by how accurate this is. Doing a little bit of statistics, I can say that I'm 95% confident that my mean height measured using this method is 1.6008 plus or minus about 0.0028 meters, which means that it's between about 160 centimeters and 159.8 centimeters and 160.36 centimeters. I will note, though, that I might not have started or stopped the very front of the iOLAB device perfectly every single time, so that is a limitation on the accuracy. Also, if I didn't move the device in an exactly straight line, it's possible that I might have added a very small amount of distance by not moving it in a straight line. All right, my second method used constant acceleration, and I used this with the iOLAB device. For constant acceleration, I decided to use the force of gravity because that is the easiest force available to me that uses constant acceleration. I used the accelerometer feature on the iOLAB device. So again, the first thing that I did was I used a board and I drew a line exactly where my height was. And then I started recording on the iOLAB device using the accelerometer feature. I held the device upright so that the y-axis was facing up and down. And I put all of this over top of a soft mat because if I'm dropping the iOLAB device, I really didn't want it to break. So that's just as a precaution. The next thing that I did was I dropped the IOLab device and I had to make sure that it bounced straight up so that it wasn't spinning or flipping over when it was being dropped. Finally, I found the length of time that it was falling, and I will show you on the next slide what this looks like on the software. I made the assumption that when it's in free fall that the accelerometer measurement is 0, and I'll explain that a little bit on the next page. I also assumed that air resistance was negligible. Um, the change that I made was to make sure that it bounced straight up after it hit the ground, because a couple of times it sort of flipped end over end and I didn't get a good measurement. All right, this is what it looks like. Was trial 1 in the iLab software. So when I was just holding it stationary with the y-axis pointing up, the device started out at an acceleration of 9.81 meters per second squared. That was the reading on it. This was when I let go of the device, and while it was in free fall, you'll notice that it was actually at 0. And this makes sense because the change in acceleration was negative 9.81 meters per second, and acceleration was constant. This little bouncy part over here is when the device hits the ground, and we don't really care about that. What we care about is this time period when it's flat after I dropped it, and we're able to find the time right here using this. When I highlight this specific section, it tells me the delta t. So here it was about 57.6 milliseconds. I also only showed acceleration in the y direction because we don't really care about z or x. All right, this is my data for this method. You'll notice that I repeated it 5 times. On average, using this method, my height was 1.609 meters, 160.9 centimeters. And if I do a little statistics, I'm 95% confident that my mean height measured using this method is 1.609 plus or minus 0.0289 meters, or between 1.58 meters and 1.64 meters. This is a little bit less precise than the previous method, but I still got a measurement that was within 1 centimeter of my actual height. So I would say it's fairly accurate. Some possible limitations is that the device might have tilted a little bit in the X or Z direction while it was falling, though I tried to minimize that. Furthermore, I calibrated the device at the very beginning of the experiment, but I was dropping it a lot, and I'm not sure that it remained perfectly calibrated after it fell a number of times. So that's another possible limitation. All right, the third method, I did not use any IOLab device or software. I used a penny and a stopwatch. So again, the first thing that I did was draw a line on a board with my height, and then I held the penny at that height line and I dropped the penny at the exact same time as I pressed start on the stopwatch. I pressed stop on the stopwatch at the very moment that the penny hit the floor, and I had to practice this a number of times to hone my reflexes because it did not go super well the first couple of times that I tried it, but after about 20 test runs, I felt like I was getting a consistent value on the time. I assumed that air resistance on the penny was negligible. I also assumed that my reaction time on the stopwatch was good, when in reality, I'm not perfect, so I know that this isn't going to be an amazing measurement. I also had to use my dominant hand for the stopwatch. I originally tried doing the stopwatch with my left hand and dropping the penny with my right, and that was terrible. So I used my dominant hand on the stopwatch. This was the data that I got. There were again 5 trials. And on average, my height actually was 160.8 centimeters, which is shockingly accurate considering I was worried that my reaction time wasn't going to be good. You'll notice that the standard deviation was significantly higher on this one, but I was 95% confident that my mean height was measured about 1.608 plus or minus 1.25 meters. So again, I'm adding or subtracting about 12.5 centimeters, which is not fabulous in terms of, a confidence interval. But considering my reaction time, I think it's pretty good. Um, yes. Oh, also, the stopwatch only measured to milliseconds. So actually, I really only had 2 sig figs. So all of these are only really accurate to the first 2 digits here. So like about 1.5 meters, about 1.7 meters, right? It isn't perfectly accurate because my stopwatch was not exact. Okay, so let's compare all of our values. My real height is 160 centimeters. I used a tape measure to measure that, so I feel as though that is fairly accurate. Under the velocity graph method, this was the most accurate method. We got 1.6008, so it was very, very close to that 160 centimeters, and my standard deviation was incredibly small for that. The constant acceleration using the IOLAB device was my second most accurate method with it was my second most accurate method, I'm going to say, considering that the standard deviation was significantly smaller than the penny method, and also because I know that it doesn't rely on my reaction time. Finally, I'd say that the least accurate was the constant acceleration with the penny method because I noticed that there was a very large standard deviation. However, if I repeated it a number of times and took the average, that actually seemed to be an ever so slightly more accurate to my real height than constant acceleration using the iLab device, so I'm surprised by how accurate this turned out to be. If I calculated an overall mean height, combining all three methods, I got 1.606 plus or minus 0.069 meters. So really we're within about 7 centimeters plus or minus on that confidence interval. I think that's pretty good. And I agree that constant acceleration does work as a valid model because both of the constant acceleration models were able to accurately predict my real height within a centimeter when we look at both of these averages here. So I think that's actually quite impressive to get my height within a centimeter. Thank you for listening to my presentation, and I hope you have a good day.